Okay, sir. So it's two. I think I should start, and then I will just briefly introduce the participants about the this session.
Okay, sure. Good.
Okay. So hello everyone. I'm T. Virupakshanan, and we are back with another Geo-Varta session organized by Banaras Hindu University Geophysical Society. This event is comprised of very fine and brief lectures by eminent personalities in the field of uh, earth sciences, and earlier we had lectures with Professor NVC Rao, Dr. Sukanta Roy, and Dr. A.K. Srivastava. We thank all the respected, and you can watch their lectures on our YouTube channel, which is SCGBHU. So, well, in continuation, today we have a very wonderful guest, Dr. Khemraj Shukla here. Sir is a computational scientist at University of Chicago. He also have worked with Brown University, Landmark Solutions, BP America, and even at Hewlett-Packard Labs. Uh, he will be lecturing us on physics-informed neural network for ultrasonic imaging. I have just searched before the session this topic on Google. So the first three links took me to his research work. So that would be really interesting to study this from him as well. So after this session, we will be having a brief question and answer session as well. Uh, and you are not supposed to turn on your mics or cameras on. You have to just type in your questions in the chat box. I will be assisting sir, and he will be answering your questions as per his convenience. We will also give you a feedback form in the chat box, so you can fill it, and the feedback form is mandatory for those who are Geo-Aakarshan participants, because we will be providing you certificates based on that. So do fill it. Also, for your prior information, this whole session is recording, and it will be uploaded to our YouTube channel, which I have already mentioned. It is a CGBHU. So because we have accommodation issues here, we have only 100 participants in the meeting allowed. So you can watch it later on YouTube. Yeah, so that's all I had to say. So, sir, please start the lecture.
Yeah. Thank you. Thank you, everyone from SCG BHU chapter. It's really good to hear from you guys that you are organizing lectures and so many outreach programs through the SCG BHU chapter and student chapter. This is really a good paradigm for everyone to learn, to contribute, and to understand what is going on at the frontier and the prolific research areas of the geophysics. So first, let me tell you that my area of the research is the geophysics. I have solved a lot of problems in the geophysics and during my PhD, but which also gave me an experience of building my strength in computational mathematics. Uh, because that was one of the key component of my thesis, and during the 6 years of my PhD I basically rejuvenated myself in the computational mathematics domain. And with that, and you know, the geophysics is pretty much mix of physics, maths, computer science, and these are not just ancillary subjects. These are, you have to be expert in all these three subjects to solve the challenging problem of the geophysics. With that, I'm broadening my horizon in the different area of the computational mathematics, like because the techniques are same. Like you take this technique of geophysics, go to the medical science and do the imaging, and take that and take this technique, geophysical tool. Like if you go in interior core of the earth, you will see the how complicated the structure is. Like it's just not the three layers of earth like crust, mantle, core, and it's there are a lot happening in that, and they comprise the fluid flow, the high temperature physics, and the convection model, and there are a lot of like magnetohydrodynamics. These are all system of equation which are very complicated to solve, and up to some extent these equations doesn't have solution. Some equation doesn't have solution. If they do, then they are not unique. So with that in mind, so I'm exploring the different aspect that how to solve this equation efficiently using the new methods. So that's why last year when I finished my PhD and I went to Brown University as a research associate in an applied math department, and I met with Professor Kaniadakish, and I just knocked his door and just told that I just told him that these are the problems which I want to solve. And then I started working on the, like, I worked for 1 year on one project, and that project is the physics informed neural network for ultrasonic imaging. Although the data is same, the wave field data which I will show you down the line, that they are exactly same what you use in geophysics for seismic imaging, for seismic modeling. They belong to the same field, but the data is acquired over a metal alloy, because these were the data provided by United States Air Force Research Lab, and these data now I'm implementing it for the same data. I'm using it with the same method for the geophysical problems. So here I will just give you a brief rundown that what physics informed neural network is and how you can use it effectively for new challenging problems which you face as a geophysicist, as a physicist, as a mathematician every day in your life and the daily job. So let's start with that. So the this machine learning is pretty much it's used everywhere as a machine learning, but machine learning, it all comes under the domain of artificial intelligence. So way back in 1947, everybody knows that who Alan Turing was. He said that what we want is a machine that can learn from experience. So like you don't have to explicitly program machine every time. So you need to have a machine which can learn from the experience. That means experience means the data. So more the data, more you will have accurate prediction. And it the machine will, if suppose entire goal of machine learning is to find the pattern in the data. So finding the pattern in the data, and with that information, with that pattern, training a machine which will give you the an informed decision on the data which is not seen by the machines. So that is all about the machine learning. So uh, uh, down the line, I will just explain you what these three terms are: artificial intelligence, machine learning, and deep learning. So with that, so what is the physics informed? So the, you know that machine learning, every day you use machine learning. Nowadays everybody has a Gmail ID, and you might have seen that when you write a mail, then it suggests you the next words or sequence of the words which you want to type in. These are all machine learning algorithm. And now if you know the face detection algorithm, and in your Facebook, you when you post a photo of your friends, then it tries to suggest you he may be or she may be in this network and like that. So those are the image recognition, and they are pretty much used nowadays, either a Facebook or go to the Pinterest or the Instagram. So all those places, all those these sites, on these web pages, you can see the application of image recognition. And then comes natural language processing. These are the natural language processing is basically the same thing which I told you in the Gmail, predicting the text. And then cognitive science and genomics is the one of the bioinformatics field where you try to reconstruct the genomes by using a sequence of the data. These all are like very much being in these all these fields, the machine learning is pretty much implemented successfully because the data is in abundance. But when it comes to the physical system, like suppose your harmonic oscillator, your seismic data, your resistivity data, gravity data, you always have a sparsity of the data because these data are required at regular grid size, and they acquiring more dense data will require you to spend more time, more logistics, more money, and like that. So we don't have a lot of data to train our machine learning algorithm in the same way like they did, like in this image recognition, natural language processing, and the cognitive science, in all those they have abundance of the data. Every day the data is coming up, and the job of machine learning is to mine those data. So the whole idea of deep neural network is to have a lot of data, the large size of the data. But since being in a small data regime, these machine learning algorithm will fail. They will not work. And task of training the deep learning algorithm is to identify a map, actually. So a map is basically that connection between the input and output. So in the machine learning terms, the inputs are the label, and the output is the features. And these inputs can have the multiple dimension. They can be of multi-dimensional input, and you have to predict a map which connects between the input and output. So you will ask a question that, do we have any map? Like, can you assure me that I will find a map which will map between these input and output? Yes, there is a theorem called universal approximation theorem, which I will explain you in a bit. But simply connecting the map, simply finding a map which connects between input and output is a very naive approach for the physical system, because physical system is governed by a very specific rules, and they are basically defined by a partial differential equation, like how you reformulate physics in terms of the equation. And for these systems, these equations are the partial differential equation. So the whole idea of physics informed neural network is how to incorporate these physics, these laws in the neural network. That is whole idea. So if we can incorporate, because suppose you want to map between x and y, and you have no idea what will be the constraint on the y. Does y satisfy something, or there is something through which we can narrow down our search space for the solution? This is whole objective of the machine learning. You have to find a solution which minimizes the difference between the input and output, and that solution will be mapped between the input and output. So if you don't have any constraint on the output, then what will happen? The neural network will try to explore a very big space where all the solutions, there will be a lot of solutions which will satisfy these kind of problems, this kind of map, the solution which you are searching. But if you put a constraint on the y, the output, then this search space will be narrowed down, and that will kind of ensure a very close to a unique solution. So that is what you want. So a few example of the physics informed system. You might have heard of Navier-Stokes equation. This is my recent interest in the research, which I have got a couple of funds approved for that. And that Navier-Stokes equation basically deals with the fluid flow, channel flow, glacier movement, and blood flow, so in the body. So wherever there is a fluid flow, in the nature there is no laminar flow. These are all turbulent flow. So wherever there is a fluid flow, the Navier-Stokes equation will come in. So how to solve that? The problem, it's also called $1 million, the millennium problem, that is $1 million problem, which is like basically this term coined by the Clay Institute. And like the Navier-Stokes equation, it seems like equation, but it is optimization problem, which I will not go in detail today, but it's a PDE. It's a partial differential equation. So everybody might have heard of Schrodinger equation. So for the defining the quantum mechanical system or nonlinear wave propagation, such as in your optical fiber, you might have heard there is a buzz about the 5G and all those the technologies. So there we are solving the Schrodinger equation to define these systems, the solution of this system. The third, which is very important, is a satellite equation, which is like predicting the trajectory and location of live and dead satellites. And the Fourth is a Berger equations. Berger equation is basically compressible gas dynamics. It defines the gas dynamics. So these and in terms of the geophysics comes the wave propagation. So how wave propagates, and propagation of waves depends a lot on the material type which you are considering, whether it is acoustic, whether it is elastic, whether it is a poroelastic, which was my PhD thesis where I worked a lot in the poroelastic. So in this talk I will focus on the wave propagation problem because that syncs with your geophysics research and your study area. So you can see that this entire system in the nature, that entire process in the nature is defined by partial differential equation. So for these physical system, you have well-defined system. If not, you can derive the system by considering all the phenomena happening in the system. So these are the things, these are the system which I'm trying to solve using the physics informed neural network. So with neural network, but physical system. So that is all about physics informed neural network. But why you have to consider this in your system? Because as Professor Feynman said, that people who wish to analyze nature without using mathematics must settle for a reduced understanding. So that means along with data, you have to care about the system of equation which is governing entire system, entire process. So without having a mathematics in neural network, you will be like searching in a blind zone, like you don't have any constraint on your solution. So that is that is which is one of the big motivation behind this study. So before I go on, so these are my research advisors. So like I was like you guys, like when I came out of institution, so I needed some advice, some guidance. So the first here, he's a Professor Kanya Rakesh.
Sir,
He is a professor at MIT and BHU.
sir, sorry to
Yeah.
excuse, but we can't see the presentation. You have to restart it.
Okay. Can you see now?
1 minute, sir. Yes, sir. Now we can see that. Okay, sir. I'm pinning it to the screen. Yes, sir. We can
Yeah.
see that now.
So where do you want me to start? Like, where did you lose me?
Sir, it's okay. We have heard all that. Just the
Yeah.
presentation was not there. Yes.
Okay. So you can see now. Just see that if presentation is slides are moving. Can you see now? It's moving.
Sir, we are on the fifth slide, I guess.
Yeah. Right now I'm on fifth slide. Now I'm going to the sixth slide.
Okay, sir.
Can okay.
No, sir.
So
We are still on the fifth slide.
you can't see on the sixth.
No, sir. It's the fifth one.
I think the full screen has an issue with the PDF. So
Sir, now the sixth slide appeared, sir.
yeah. So there is an issue with the full screen. So I will
Oh.
just keep it like this. So
Okay,
okay.
sir. That's not a
Okay.
problem, sir. Yeah.
Okay. So these are my advisors, my research collaborators, my mentors. So the first pick which you see that he's a Professor Karya Rakesh. He is a professor at Brown and MIT with whom I'm working right now. And he was the person who invented physics informed neural network. In 2017, he published 2 papers. You can just go and Google that his name and it will come up. So it's the most cited paper on the physics informed neural network. And the next is the Professor Hesteven, who was my exchange study advisor, with who gave me a foundation on the numerical analysis. And he's the Dr. Carcione from OGS Italy. He's a geophysicist, and he helped me a lot in deriving the wave system, how to derive the wave system, the wave physics system for the fully fluid flare. And he was my committee member, the Professor Jesse Chen from Rice University. And Professor Martin De Hoop, you might have heard that he's a very famous guy in geophysics. He derived all the green function kind of stuff. And he's a Professor Priyank Jaiswal, who was a collaborator with us, and he's a now professor of geophysics at Oklahoma State University. And so these are all my main core advisors and collaborators, and with whom I worked. And without their advising suggestion, I could not have come to this work and the conclusion. So let's start. So the outline of my talk is I'll start with motivation, then I'll just give a brief about what is a physics informed neural network, and then I will start explaining the pin. So in the acronym of the physics informed neural network is PIN, so like physics informed neural network, and then I'll go to physics informed neural network and ultrasonic imaging. Then I will just wrap it up with some concluding remarks and summary. So let's start with motivation. So everybody, now in seismic imaging, most of the imaging techniques are based on the acoustic wave equation. So acoustic wave equation is basically, in this approximation, the medium is approximated as a fluid. So you don't have shear actually. So this system is defined by two equations, Hooke's law and Newton's second law of motion. So Hooke's law, you know that this is the stress proportional to strain. So since it is like a fluid, so you just go for the hydrostatic pressure. So the stress is basically the pressure, and this is basically the gradient of the pressure. Left side is basically rate of change of velocity. So that is the equation of motion. If you pair these two equations, Hooke's law, you will get a system. In the first order, it will be in terms of the pressure and velocity. In second order, it will be just displacement. So right side, you can see this is a snapshot of the wave field. This is acoustic snapshot, and you can say there is only one wave front, which is P wave, and that is compressional waves. So this is very simple and most used approximation for all the advanced imaging method, whether it is the pre-stack time migration or depth migration or VSP modeling or anything. Because first of all, you'd go for a very large scale, then solution computing the solution for this system is cheap, and most of the time you deal with the vertical component data, the geophone data, the vertical component data. So they are basically the pressure, and most of these motion is basically dominated by the vertical component of the displacement or the velocity, particle velocity. So you have just one component. So if you show a little bit more courage, you will go for elastic approximation. There things become more tricky and more compute intensive. So in this case, you consider your medium behaves as a solid, and in that case, now you have stress, which is tensor, no more scalar like pressure. And that, like, I mean to say, the scalar means the only one, the stress component was defining the acoustic wave equation. Here you have a stress tensor, which is 6 component in 3D and 3 component in 2D. And then again, the same equation for equation of motion. So the left side is the basically divergence of stress, and that is equal to the rate of change of velocity. So that is Newton's second law, and the first is Hooke's law. And if you take the time derivative of Hooke's law and pair this up, then it will come up in system of equation which has 9 coupled PD in 3D. So you are solving the 9 field variables, 3 particle velocity and 6 stress component, which in case of acoustic was the 4 component. So you can see now you are just the system has been just doubled. Like the unknown which you will be computing, that will be taking much more time and much more resources. But in this case, you will be capturing more accurate physics. So here you can see the first wavefront, the fastest moving wavefront is the P wave, and the wavefront which is trailing behind is the shear wave. So you have a both here, compression and shear both. So you have both waves, and because of these two, the compression and shear effect, you get both waves. But this is not the case you actually encounter in this in the rocks. You have a porosity, you have a permeability, you have a fluid. So what would happen if you want to incorporate those 3 systems? So those systems are called poroelastic systems. So suppose if you want to go on the reservoir scale, so like in the scales of meter, so you have a frequency of investigation around 10 hertz to 100 hertz. Taking 100 hertz is a little bit more optimistic, but I'm just considering it a little bit more more wide band of the frequency. And here right side you have the rock physics model, the 3D rock model, which have micrometer scale. Why I'm showing these two pictures is because suppose you want to excite this the reservoir scale model, and the fluid flow in this case will be different than the fluid flow in the this rock physics model, because and the rock physics model you are exploring at the frequency of kilohertz to megahertz, that is a sonic frequency, and here your frequency is 110 hertz, 10 hertz to 100 hertz, 10 hertz to 100 hertz. And that's why the suppose with if you have a pulse and you excite the domain with 100 hertz frequency, in that case the it will induce the motion in both solid and as well as in the fluid. But while considering the rock physics model, the right side image, and you are taking a pulse of megahertz, suppose 25 kilohertz, which is sonic frequency for the acoustic logging. So in that case your fluid flow nature will be different because you have a higher frequency, and for both fluid flow you will have a different set of equations and different set of system which you will be solving. So let me tell you that how the fluid flow looks like. So for the low frequency range, the fluid flow is like laminar. It flows like this. So you can see it flows like this. This is the laminar flow where the fluid is like in the layer, and the velocity is linearly varying if you go from the bottom layer to the top layer. But if you go to the high frequency range, if you go to the high frequency range, then the fluid flow is no more laminar, it's a turbulent. So that is hard to define and the high frequency range. But since we are not focusing here on this kind of that how we define this, so I just wanted to give that how this the system of equation, they are different for different material, and when you keep on incorporating the different factors in the rock, then the system of equation changes. So now you remember how in the elastic wave propagation in the snapshot you had two waves like P wave and shear wave, but for poroelastic material where you are considering both porosity, permeability, fluid flow, and now suppose you consider the viscosity of the fluid is 0, and this is orthotropic sandstone, that is anisotropic sandstone, which has a two orthogonal axis of symmetry. Like your velocity will be varying with respect to direction, and it will be faster and slower along orthogonal directions. So this is a snapshot of the poroelastic wave equation, solution of the poroelastic wave equation. So you can see there are three wave fronts. The first is the P, then second is the shear, and then third is it is called slow P wave. This wave mode is generated due to the relative motion between the solid and fluid. So you can see now the complexity. You incorporate more factor, you throw in more factor, more parameters, your system becomes more complicated, and you get more feature, more accuracy, more approximation. So that is the poroelastic wave equation. So this is basically the horizontal component of the particle velocity left side. This is the vertical component. So in the horizontal, you can see the polarity change. If you see the left side and right side, there is a polarity change in the wave field. That is because it is a horizontal component. So and your motion is described by a vector. So on the both side opposite, and on the if you take this as a zero axis at 10 meter on both side, your waves will be going in opposite direction. So that's why you have polarity change. But that is not the case in the vertical component. So this is basically three main equations which we consider in seismic imaging, seismic modeling, and these things are used for estimating the rock property and the quantification of the reservoir in terms of the porosity, permeability, and the resource estimation. So one more example I picked out from the epoxy glass material. Why? Because you can see, if you will study, maybe you might have studied, there is a triplication pattern in the shear wave. So this you can see when you go in the if you simulate in epoxy glass kind of material, where you have P wave and then shear wave. You can see there is a triplication clearly. Can you see my cursor?
Uh, yes, sir, we can see that.
Yeah. Yeah. So you can see there is a triplication, and then you have a slow P wave. So this is the, you can see the anisotropy, how anisotropy and and the porosity, permeability affects the wave propagation. So you can see the left side is horizontal component and right side is the vertical component. So these are the basically model which we use, and then how we solve this system. In the current state, we use different numerical approximation to solve this system. The most adorable method is finite difference method. So it's very simple and it's very easy to use, very easy to implement. You Google, there will be a lot of material on that. But the method which I used, it's a very high accurate method, high order method. It's called DG methods. So I will just touch down that what this method is. In this basically method, what you do, you take the domain, discretize it in terms of the, discretize it with the triangle or tetrahedral. Tetrahedral in 3D and triangle in 2D, and they are called unstructured meshes. And why we do that? In finite difference, you can't capture the irregular topography because your grid has to have the square or the rectangle. You cannot capture, and in order to capture those kind of irregularity, your grid size has to be very small, and that will increase your computational cost. And second is that accuracy. Accuracy for these method is much better than the finite difference method. So this is just a 3D model for acoustic wave. You can see there is an interface here, and from the interface you are getting a reflection and you are getting a direct wave and the refracted wave going in the second layer. And you can see that on the both side of the interface, the size of the triangle, the size of triangle is different. In the first layer you have a more tetrahedral, and in the second layer you have a less tetrahedral because they are coarse. So this kind of adaptivity is very much handy in this kind of method. This is called discontinuous Galerkin method based on the finite element method. So first, the first property of this method is that you can handle irregular geometry, and second is it has a very low numerical dissipation and dispersion. Dissipation means, like, suppose red is your actual solution, and if you go for the low order numerical scheme, you need to have first a lot of grid point, and you will not exactly reconstruct the actual solution because there is a numerical dissipation that comes when you these kind of terms are very pronounced when you go for the numerical analysis. Dissipation means due to the since these waves keeps on propagating, and they are energy stable scheme, and as the time period increases, time period for the propagation increases, then there is the solution gets dissipated because there is some stability condition for that. So but for DG methods you can have very less dissipation, and this is how DG methods look like for the same scheme. If you use the low order scheme like finite difference second order, and you can see there is and in spite of having so many grid points, it never recovers the actual solution. But for the DG, with less number of grid points to recover more accurate solution, that is the second and most important the property of the DG. Third, that if you increase the number of element or number of grid points in the element, the accuracy of solution will increase. That is the beauty of the DG method. So more elements, more accuracy. If there is a more grid point in the element, the accuracy will be more. And the fourth is the computing purposes. These methods, DG methods, are very much suitable for today's computing paradigm, which is GPU. So general purpose graphical processing unit, GPU computing. So if it is a very low level programming paradigm, but it brings down, like in my experience, the simulation which take like 8 CPUs around 72 hours. So with one GPU, if I spend $850, I brought it down from 72 hours to 6 minutes. So that is the kind of flexibility DG provides with the GPUs. So these are the methods, but these methods require a lot of bookkeeping, a lot of the desk work, a lot of back of enveloped calculation to do the numerical simulation, because first you take a model, then discretize it, then parse it, then take it to the solver. You have a solver ready based on your numerical scheme, then run your solver, and then again get the solution, and then parse it. Then all the snapshot which I showed you, it comes in. But suppose if we do have a real world data and we don't want to do this, can we use the neural network if I know the equation? So that is the whole idea for the next section of the talk. So before I go in, if there is any question, just how will it work, Vishal? Means will they ask question at the last? And I don't want to lose them. So if they have any questions, so.
Yes, sir. We have set for the question and answer session at the end of the lecture. So they will be writing their questions in the chat, and I will be telling you about that.
Yeah, sure. And if you have a slide specific question, there is a slide number on the bottom of the slide. Please refer that number. So that will be helpful for you also to go back and forth between the slides. So.
Okay, sir. Sure, sir.
Sure. Okay. So now come to the physics informed neural networks. So having said that, these are the equation which you solve in the geophysical problem, seismic problem. Sorry, there I am just taking the wave physics problem. The similarly can be like translated for the gravity magnetic problem, for resistivity problem, for the well logs problems. All those can be translated in terms of PD, and you can use same approach as long as you are considering the neural network. If they are in PD, you can use any discretization scheme. So let's go for the physics informed neural network, and I'll tell you how to solve these equations. So before I go dive into the physics, so there is always a question: what is difference between the artificial intelligence, machine learning, and deep learning? These are all like misnomers for many things. So artificial intelligence is basically where your machine thinks like a human brain and it works like a human brain. We are not yet there, but you have seen these movies, the Terminator, T-800, that Arnold Schwarzenegger plays that role. So these are basically we are going to achieve. So last year or last year, there was a conference, Davos in desert, I think in Saudi Arabia, and there they showed almost they achieved this AI. It's called Sophia. Just Google it. It works, thinks, walks like a human. So that is all artificial intelligence, and but we are not yet there. Machine learning. Machine learning is basically a term, a sophisticated term for the data mining. So what in data mining we do? We have a data. We try to figure out what is the pattern in the data. We analyze that data, and we get an idea, we have a model, and then we try to implement that idea for the data which we have not seen. So that is a machine learning. So with having gaining experience based on some data and then applying that on the data which the machine has not seen, and the machine will done it automatically by itself. That is called machine learning. And what is deep learning? Deep learning is subset of machine learning. It basically, if you see the definition, the deep learning, they just write in the very famous book of Ian Goodfellow on the neural network that deep learning equal to more compute, more mathematics. I think it's slightly more than that. So in deep learning is a technology which is used to solve the machine learning problem. So suppose, just take an example. Suppose you have a machine learning algorithm, you have a machine where you said that if someone says it is dark, then the flashlight should be on. So what machine learning algorithm will say that anyone says dark in English, and then the machine learning algorithm will switch on the flashlight. But if someone says that I cannot see it because the light is very dim, so he also wants to switch on the flashlight, but machine learning algorithm will not do it because it is just trained for the the dark text, and then there comes the deep learning, which, if suppose machine learning algorithm predicts the inaccurate result, then user has to go and correct it explicitly. But deep neural network, our deep learning model, they will correct it by themselves. So that is the difference between the machine learning and deep learning. Second difference which comes is the data dimensionality, like high order data dimensionality, which is easily dealt by the deep neural network, and the complex mapping between the input and output with a lot of non-linearity. So whenever there is a non-linearity between input and output, then deep neural network comes in. So one of the example of machine learning is Spotify. This is online music streaming platform. If you have listen some music, on that basis, it will recommend you to a list of it will recommend you playlist based on the others user experience. So what it will do, it will see that if other users, they have listened this song, if they have gone for this song, then what they have there in playlist based on that song. So that is basically recommendation from the Spotify. Second, third, which where deep learning comes in, during my work experience at Hewlett Packard, there was the Uber, which was next building, and they were doing a lot of tests on the self-driving car. So self-driving car, what they used to do, like they have a very controlled playground kind of stuff, and when self-driving car, it hits any barricade, then it will correct itself. It will come back and then go to the take the path where there is no barricade. So something like that. So deep learning algorithm, they correct it by themselves by adding more data. So these three are the basically the machine learning and deep learning are basically subset of AI, but they are different. Deep learning is a tool to solve machine learning problem. So I hope this is clear, because this is a very foundation of the machine learning and the PIN, actually physics informed neural network. So any problem in the system, physical system, any problem, like I'm saying it like without any constraint and without any restriction on any riders, any system, the first order system, you can write in this form. The rate of change of the field variable, it could be your density, it could be your density, it could be particle velocity, it could be displacement, whatever you want to represent it with. This rate of change of time rate of change of that, plus this n, basically the calligraphic n is basically nonlinear operator, and that is a function of u and parameter of lambda. Lambda could be your wave speed, your Lamb's constant, or your modulus of rigidity, or bulk modulus, whatever you want to take into that consideration. So this is the first order system, first order PD, which represent a typical physical system, and you can write every system in this form. There is no rider on that. So here I have explicitly explained what calligraphic n function of u and lambda means. That is a parameter ux. X is a spatial derivative. U sub x is basically spatial derivative, partial spatial derivative of u, and similarly you can see that somehow the combination of linear combination and non-linear combination of u time rate change of field plus space change of the how that varies with the space. So everything, suppose you want to conserve the mass, you want to conserve the energy, so that thing you can write in terms of the time, in terms of the space, and then add it up. That is whole, and this is called conservative system or energy conservative system. Or if you have a dissipative system, then suppose where energy is being lost, then on the right hand side it will not be zero, it will be some a low order term in case of the wave propagation. So what we are trying to solve in the pin, so suppose I am given with lambda, the parameter, suppose I am given the wave speed, and I want to ask you that in that domain how the wave field looks like, and this is your pretty much forward problem. So given the parameter, the material coefficient, you are computing the wave field or displacement field or velocity over the domain. Now the most important things comes in. Given the wave field, you want to compute the lambda, which is basically the inverse problem. So you have a seismic data in terms of the, suppose, acoustic wave approximation. You have a traces, the seismic traces, and you want to compute the speed that is generally required. Velocity is a more important component in any seismic imaging things. So how to compute that? So there comes the pin, and you don't have to do a lot of changes in the code going from forward to inverse problem. It's very simple, but the takeaway from this slide is the problem definition. Given the parameter, how you complete the wave, how you compute the wave field. Given the wave field, how you compute the parameter in the equation. So all those PDs are parameterized. So you have to come up with such a model which will, such a PD which will explain your physical phenomena. Now going ahead, how does neural networks look like? So in one of the online courses from Stanford University, they said the machine learning is the science of getting computers to act without being explicitly programmed. That means your model is learned, and for a given input, it will predict what would be the output. So in the typical world, in the conventional world, so in this equation, what is your input? The input is your domain spatial coordinate, that is the domain, and time. These three will be input, because your rate of change of your wave field is with respect to time, the first term, and the second one is with respect to space. So your input will be spatial coordinate and temporal coordinate, and output will be u given lambda. If you don't have lambda, you have u, then your output will be lambda. But if you see the neural network architecture, you have an input layer, and each input, these circles represent the input component, that is x, y, t. And then you have a hidden layer. Here I have just shown two. These are not the deep neural network, but just for sake of example I just took. And you see that there are 4 neurons, 1, 2, 3, 4. That is also the width of neural network, and this is 2-layer deep, that is the depth of neural network. And each layer and there are also these are the 4 neurons, and you see that each input is interacting with each neuron, and they are multiplied with a weight value. So when this input, the x, comes to this neuron, it is multiplied by a weighting, the weighting coefficient, and similarly for y, and similarly for t. And then when it goes to the next layer, again the same thing is done. This is multiplied by weight, and then goes to the next layer, and then it finally comes to the predicted output, which is basically w x plus b. B, forget about b. B is a bias, but you can consider b as a kind of weights. But your predicted output is basically a fine transform in terms of the linear mapping. So what you take the input, you take x, y, t, and you multiply it with a weighting matrices. For neural network, the weight matrices are generated randomly. So this is all you have. If you stop here, so what does it look like? It is a regression problem. It is just the linear regression. That's it. But this is not what you're here for. You don't want to spend so much compute power to do the regression. So next comes your activation function. What you take this output and multiply with some kind of activation function. So suppose this is your input x1, x2, and each x1, x2 is basically multiplied by with a weight, and then goes to this hidden neurons, and then comes to another layer called activation function, that is a junction basically. So let me explain what is activation function. What does activation function means? The definition of activation function is basically they incorporate non-linearity in your output. So if you remember this, this is a linear. So when you operate it with activation function, suppose your activation function for time being is sine. So take the sign of this, and that basically it incorporates. So you see the nature of the sign. So it brings in the non-linearity. So if you have a very high dimensional data, then what activation function does, in mathematical term, it represents the high dimensional data in the low dimensional form, and then give a more and approximate a more complex function with a very few low dimensional input. But yeah, okay, there are a lot of buzzwords in that. First, so understand in the physical way. So neural network works like your brain works. You have a neurons, and every neurons, when it is provided the information, then what it does, so neurons, they basically collect the information from each neuron and comes to the junction. So just like multiplying it weights and come to a junction, and they will decide, and then they will decide if the output coming from this particular neuron is enough to fire up the neurons. So that is where activation function comes. What activation function decides that whether I need to fire up this neuron, this particular neuron or not, whether it qualifies for the firing or not. Because activation function, if you take, these are the examples, they basically go from -1 to 1, like suppose sigmoid. In case of ReLU, they go for 0 to 1. So basically they put all the output between these two, 0, 1 or -1 to 1, these limits. So they will just see that whether your neurons, the value at the neurons are not exceeding the limits, they are well within the range, and they need to be fired. So that is why activation function is important. And when it brings in the non-linearity in your output, then it's easy to compute the derivative. So suppose if you want to maximize this function, the second derivative will be 0, and it's done and dusted. But when you bring in the activation function, then you can differentiate it for optimization purposes or for finding the maximum of the cost function. So these three things, now you have input x, y, t, you have a neural network layers, and then you have a activation function. When you apply everything, then you get an output from the neural network. There is no physics yet in this neural network. Now, if you don't have a physics here, I'm not talking right now, I'm just talking about basic neural network. Now you have an output which is y, that is wx plus b, and this is supervised learning, like you know the solution for that particular x, y, t. Now you take the error between these two, the output predicted by the neural network and actual output. When you take the error and then you try to minimize that error, to minimize that error, what will you do? You will take the take the first derivative, make it 0, and take the first derivative with respect to the weights, because your neural network is defined in terms of the two model parameter, weights and bias. So as I explained earlier, so these w and b, so given once your model is trained, so for given x, y, t, you can just compute what would be the output. For that you need to know w and b. So once you get your error function, so take the minimize that error with respect to w and b. So once you get that, and then you keep on updating the weights and bias for every iteration. So you take the error, then this is what it does. Forget about eta for now. Eta is basically learning rate. which is in neural network terminologies, it's called hyperparameters. So hyperparameters means there is a, you have to choose, you have to tune it. There is a no set rules to compute these coefficients. So for timing, forget about that. So this is basically called gradient descent model. So you just take the error with take the derivative of the error with respect to weights, and then again back propagate it. So you just subtract W1, the previous W1, minus eta of eta, suppose eta is 1 for now, minus W partial error by partial W1. So in that way your weights are updated. So once they are updated, then go again for the next cycles. So this is how the neural network optimization works. So far I have not explained any physics yet. Okay, so now where comes the physics? So let me go back a bit. So I say that U predicted is solution of any PD. So if U predicted is solution of PD, so how do you check if this is a solution of any equation? You just plug in those value in the equation. That is exactly what I'm doing here for pin. Once I got U predicted, I plug that in the PD and then see that how far off we are. So if your PD is like this and you got from the neural network, you plug in here, you take the time derivative of U, and then whatever the nonlinear operator is here, and just see that if that goes to 0 or not. If not, then again go for the second iteration. That is, this is exactly what you have to add in your error function. So let me see the example. This is one of the typical the fluid flow field actually. So you have a UTX, that how the fluid flows, and this is basically F basically is the PD. And what I'm trying to do here, MSEU, that is error due to the data. Like you have a data and the error like predicted by the neural network minus what is the actual solution there. That is MSEU, mean square error from the data. And then comes mean square error from the physics.